Okay, hello. I'm Kazuki Yoshizoe from RIKEN, and I'm from RIKEN Center for Advanced Intelligence project, which is working on AI. I'm also a researcher at the RIKEN R-CCS, so this is here. I do work both on AI and HPC. And today I will talk about two things. Both are related to the AlphaGo program, which is probably one of the most remarkable achievements in recent AI. And how many of you have heard of AlphaGo program? Thank you very much. Most of you have. So it's a program which plays the game of Go, which is developed by a company named Google DeepMind, which is probably the most famous company in AI. And well, it's based on two breakthroughs. One is Monte Carlo tree search, another is, of course, deep learning. It beat former and current human champions and also other top 3 professionals in a remarkable record of 60 wins and 0 losses. And now it's clearly superhuman. And so it's based on 3 techniques, mainly deep learning, Monte Carlo tree search, and reinforcement learning. And these are all very interesting topics. I will focus on how to parallelize these two, that is graph search and deep learning. Okay? So first topic is about parallelizing graph search. So what I mean by graph search is that, so given a graph, our goal is to find a set of nodes or some set of paths. And so, well, for some problem, of course, this means a shortest path, or sometimes this is kind of an optimal combination, or of course, this can be the best move in games like this. All of these problems could be solved by graph search. And some are, so for some problems, graphs are explicitly given, like roadmap trains or social network graphs. But for other types of graph search problems, like combinatorial optimization, or of course games, or SAT solving, or constraint satisfaction problems, graphs are not explicitly given. Graphs are generated by rules on demand. And today I will mainly talk about this one. Of course, game is one of them. Okay. So when it comes to parallelizing graph search, it's not so straightforward. The reason is that practical search algorithms will not exhaustively traverse all nodes. That's impractical for larger scale problems. What we do is that we prune unpromising branches of the graph, like shown here. So what happens is that the graph, or maybe it can be a tree, that it's highly unbalanced. So a very naive approach like this, assigning some of the subtrees to different compute nodes, will result in a highly unbalanced workloads because for some compute nodes, the graphs are pruned out and there will be no workloads. So it doesn't work in practice. But there are ways to parallelize some of the useful graph search algorithms. And one group is depth-first search related things. And another is more popular maybe and useful. Things like A-star search used for shortest path search or Monte Carlo tree search. It's famous for the game of Go, but it has lots of applications. And we need 2 different types of method. I will focus on 2 examples from DFS and mainly MCTS for this approach. So for when we want to parallelize graph search, for simple graph search, in case that each graph node is visited at most once, then it's actually very simple, and we have a simple and efficient way of parallelizing this type of algorithm. It's not so well known. People often think it's impossible, but actually it's possible. So this is, well, probably a depth-first search variations, and I will show how to parallelize this. And also for other graph search, including Dijkstra-like algorithm, that's Bellman-Ford, or A-star search, or Monte Carlo tree search, nodes are visited more than once. So in this case, we need a little bit different technique, and I will briefly explain this one as well. Okay? And I think it doesn't look like a depth-first search application, but these are actually depth-first search problems. Have you ever heard of a BIA diaper problem? Maybe no. So there's a story about Walmart that on Thursday night, people tend to buy beer and diaper together. And so they put these products in a close shelves, and it increased sales. Well, it's a story, and I've surveyed it, and it's not true, but it's very famous. So it's often used as for explanation. And so it's like this. So given a database of market basket data, and these are items, these are contents of each basket. Our goal is to find out something like 146. It's bought 3 times and includes 3 items. So these are interesting ones. This could be solved by depth-first search. And we've been working on some problems applied to genomics problem. So SNPs are one of the flips, and the SNPs are flips in our DNA sequence, and which might result in some genetic disease. And our goal is to find out not a single SNP, but combination of SNPs, which might be the cause of some genetic disease. And it's really a time-consuming problem. If we apply some naive algorithm to this, the complexity of the problem is like 2 to the number of SNPs, and that's like sometimes 2 to the million, and of course it's not possible. But there is a smart algorithm which does prune out most of the unnecessary part of the tree. And we have parallelized this. And these are all depth-first search. Okay, so when you want to implement DFS, probably the natural way is to use a recursive function call like this. So you call a function, you traverse down one edge, and if you return from a function, you backtrack once. And this is a very simple recursion-based depth-first search. The problem is that it's very difficult to parallelize because every step of the function call relies on the previous result of the function call. So there's no place for exploiting parallelism. So what we have to do is that so we can, for some problem, we update the thresholds. So this is more practical. So we update the threshold, so we prune the branches more in the later stage of search. But overall, we only have update threshold thing and do something. And all the complex things are in this do something line, update threshold line. Other structure is, well, very simple. So how we parallelize this is we have to change the algorithm so that we can exploit some parallelism. So this recursive function call could be changed to loop-based code by using some stack approach. So probably you know that if we do function call, we are maintaining some function stacks on the memory. And we do that manually, but in a little bit different way. So this code can be modified to this. Maybe you don't understand what I'm doing, so I can illustrate here. So this is the original recursive function call. This is a loop-based one. So what it does is that for recursive function call approach, we do go down the tree and backtrack and visit another node and backtrack and traverses all the nodes into tree. And what we do for this loop-based approach is that we push the root node onto the stack. And after that, what we do is pop this node and push the children of this node. So we pop R, we push ABC. We pop A, we push BC. We pop D, and we push FG. And when the stack becomes empty, then it's doing something almost equivalent to this one. So in this type of reformulation, we can get loop-based code. And so, of course, we can parallelize this part. And so that's actually what we do. There are some small remarks. If you are interested in the meaning of this, please ask me later. So now we can forget that we were working on search. So all we see is that, each process pushes something to the stack and pops something from the stack. And so then each process has its own stack. So if one of the process has an empty stack, it requests the workloads to others. So it's a simple work stealing problem. So it's, well, I think you have an old history in HPC about workload stealing. And by combining some of the recent work, which is based on hypergraph and random edge, so which reduces the diameter of the topology of the graph, I mean, so that you can reach any compute nodes in a small number of hops. And we just request to the compute nodes connected with some graph. In this case, we use hypercube and random edge. And this is very efficient. And also, we have to do broadcast and reduce some global information. And of course, we can rely on some tree-like topology. And we do these at the same time. We do work stealing on some hypercube-based graph. We do work stealing on tree-based, and we send global information on tree-based topology. And these are almost done. But then we have to add one more thing, that's distributed termination detection. And this is one of the things which is surprisingly difficult for distributed parallel environment. It's just detecting the termination of the entire code correctly. So the code will end if all stacks are empty. And just to guarantee that, we need some algorithm which relies on some proof that it's correct. Well, if we integrate all these in an algorithm, also this is just for reference how we solved a genetic problem. So I'll upload this later. So in case you are interested, please read these papers. So this is the performance we get. So we are solving some of the genetic problems for analyzing Alzheimer's disease genes, or trying to find out genes which are genomes which are specific to Japanese people. And the original problem takes, in this case, like 48,000 seconds. And if we use 1,200 cores, the speedup is it's almost linear. In this case, it was 1,175-fold speedup, so it's almost linear. It's very good. So in general, if the original problem takes long, then speedup is almost linear. If it takes only short time, then of course there's some limit here, but it's not so surprising. And it's not published, we didn't publish it. But last year we had used K-computer, used about 140K cores, and we've obtained estimated speedup of around 110 or 120K fold, and that's very good for a graph search algorithm. Okay, that's DFS, and I will talk about Monte Carlo tree search and A-star search. So A-star search, well, it's a Dijkstra's algorithm with evaluation function. It's a very useful algorithm. It's all 50 years old, maybe 51 years old, and has lots of applications. It's used. Still, it's used for many problems, like shortest path. Like in the past, it was used for DNA sequence alignment or these things. And Monte Carlo tree search, it's a new algorithm developed in 2006, originally developed for the game of Go, but now it's applied to many problems, including two-player games, multiplayer games, real-time games, and natural language processing, biometric security, schedule, and lots of problems are solved with MCTS. And what do we need for this type of non-depth first search is that what happens is that you can reach the same node with a different path. So if you do nothing smart, then you will do the same search again from here. So what you normally do is to record the results in a hash table. So when you visit the node for the second time, you look up the hash table and you reuse the result. And this is a very popular technique. So for this type of algorithms, well, like we do have something like this. For A-star, we have priority queue. For Monte Carlo tree search or iterative deepening A-star, we have hash table. So in this case, what we do is that we distribute a hash table based on some hash function. This is a simple distributed hash table. So it's like, so given a number of compute nodes and given the graph, in a sense, we colorize the nodes of the graph based on some hash function, kind of a random hash function. And if it's 1, 1, then it goes to 3. If it's 2, it goes to this. And if it's 1, it goes to this. And so this approach is very simple, and it will achieve almost uniform load balancing if the hash function is designed for it. But of course, it has one drawback. That is, it's easy to see that if you traverse one edge, almost always you will have to send a message between different compute nodes. So it's a trade-off. So we get uniform load balancing, but we have frequent one-to-one communication. So we have to measure if it works okay. And in fact, it works very well for many problems. So it's a benchmark problem solving slotting puzzle or Rubik's Cube. This is a very old work published in 1999. At this time, they used 128 nodes. The speed up was almost linear. And there's a work about ASTO search. So it's not based on hash table. It's based on a distributed priority queue. The result was a bit complex, but in the best case, it achieved higher than 1,000-fold speedup using around 2,000 cores. And this is our work about parallelizing Monte Carlo tree search. If you parallelize those benchmark problems in the real Go program, and the speedup was like this. In this case, like 3,000-fold, and for real Go programs, it was like 1,300-fold using 2,400 cores. So it's very good for this kind of complex graph search problems. So, well, in short, you can parallelize a graph search problem. So in case of need, please try looking at existing work. So you don't need to give up. Okay, then you are maybe more interested in deep learning things. So I will briefly talk about deep neural networks. I think many of you already know this, so it might be boring, but please forgive me. This is just a review of recent development of deep neural networks. So deep learning can do many things: image recognition, natural language processing, sound, voice recognition, or generation. We are trying to solve material science problems. There are many people trying to solve material science problems. Of course, there are many research related to games. And this is an example of deep neural network ability. So this was 2015 result. You see the bounding boxes on these objects has probability of being a human is 0.998 here, 0.987 here. And these are all already very good. Well, one surprising thing is that here's something. Probably it's a knife, but it's half hidden. It says 0.60 knife. So, well, it's some ability to guess it's not a fork, but it's a knife. But also, it makes some mistakes. If you focus on this part, it says it's a book, 0.83. But of course, it's a birthday cake, right? We can understand that from the context. But these mistakes are more, well, kind of understandable. If you just focus on small region, maybe human beings might misunderstand this. And this is the state-of-the-art result in 2015. This was achieved by a model called ResNet, which is one of the most famous neural network models used for image recognition. Okay, maybe you know what a neural network is. Well, it was proposed long ago. It's imitating the human or animals' neuron behavior. If you have a small input, we produce small output. If we have larger input, then we produce large output. Traditionally, we've been using sigmoid function here, but now we are relying on this ReLU function, 0 until here, and y equals z from here in the positive region. And we can, so in old ages, we had only 3 layers, input layer, output layer, and 1 hidden layer. But because we are working on deep neural network, we have more number of layers now. And one important thing is this. This is convolutional filters. I think many of you have tried to edit images like using these kind of tools. How many of you have tried to blur an image or detect edges of an image or something? Oh. Thank you. So this could be done by a very simple calculation. So if you calculate this, so this is multiplying 1 to the pixel surrounding 1 pixel, multiply -4 to the pixel value, and take the average, then only the edges remains. So this is edge detection based on convolutional filters. And well, it can detect, it can do many things. It can blur, it can emboss, or it can do many things. And neural networks can do this. This is what we call CNN, convolutional neural network. And we can make it recognize handwritten numbers. It's an old technique, so it it was possible almost 40 years ago. So if we use small number of layers, we can detect handwritten numbers based on the filters such that, so we can make a filter which detects vertical lines. We can make a filter which detects horizontal lines. We can detect other shapes like corners or something. And based on these filters result, we can calculate the probability of this symbol being some numbers. And of course, there are only vertical lines and no horizontal lines, no corners or something. It's likely to be 1, right? And if you have a little bit of horizontal line, vertical line connected with a corner, maybe 7, like that. So intuitively, it's understandable. And so very simply saying, the difference between that shallow neural network and the recent DCNN is that it has more number of layers. It's just that. Now, there are a lot of details which make it possible. I will skip that. There are lots of good resources on the internet, so please read these if you are interested. But intuitively saying, what we can do is that imagine we apply edge detection in the first layer, and then we detect the vertical lines. And we can apply this technique to colorized images, right? So it's like that. So if we have a large number of layers of simple filters, we can detect complex shape like this. So this is called cat face neuron. It's described in a paper published by Google. So if we have a large number of layers, one of the neurons here is, gets, how do you say, it says it gets excited with this image. So of course it can detect cats. The number of layers used in neural networks tend to increase. And at 2015, the famous model ResNet 152, of course, has 152 layers. And this was the state of the art. And recently, ResNet 50, which has, of course, 50 layers, it's popularly used for benchmarking the deep neural network training. And the output will be like, so in case of object recognition, something like dogs, 94%, cats, 3%, aircraft, 1% or less, or something like that. So this is what's done for recent image recognition. This is just a demonstration of the ability of the neural network. So it's applied to game of Go. This is a game of Go. I'm just selecting the point with the higher probability. It's trained based on human professional moves. It's just guessing the next professional move. And it's like object recognition. So instead of giving a probability to cat, dog, or airplane, car, or something, it gives a probability to the next move. And just by selecting the moves with a higher probability, it's able to play the game at a strong level. So it's surprisingly strong. I mean, it's just based on the prediction of neural network. I think if you start playing Go now, I think you need to train maybe 2 or 3 years to beat this program. It's surprisingly strong. And well, it's just based on the prediction of neural network. So if you have a GPU, it takes only 2 or 3 milliseconds to compute. Okay? But then how do we train this? So this is a typical way of training neural network. Well, it's not only for neural networks, but for machine learning methods. So we do prepare training data, in this case, mostly images. And what you do is we shuffle and extract a mini batch, which is a small subset of the training data, like some hundreds of images. And we let neural network to predict. We call it forward. And of course, the initial phase prediction fails. So we can compute the error. And we can calculate the gradient based on the error, and we update the weights in the neural network. And so this is one forward and one backward, and update weights. And we repeat it until the accuracy stops improving. So we calculate the accuracy based on a separate set of data, which is often called test data or validation data. So we observe the training error and validation error and stop and repeat the process until the validation error stops improving. This is the typical learning curve of the training phase. So you see, because of the limited number of images in one so-called mini batch, This is very noisy. We only look at a subset of the images. So of course, if you're unlucky, there are large loss. So what we do is that we set the learning rate, which is, well, the multiplied gradient to learning rate. And normally it's set to a small value, 0.01 or smaller. And during the training phase, it's gradually decreased. And we do it until it stops improving. It takes very long time. And so when we want to parallelize this, one intuitive idea is to make the mini batch size greater so that we can parallelize the training phase. We can get more accurate error in a short time. And in fact, it's effective for many non-deep learning machine learning algorithms. So if we have, say, intuitively we increase the size of mini batch, our loss is more accurate. So we can increase the learning rate. That's an intuitive approach. And it works well for some other problems, but, well, it doesn't work for deep neural networks. So this is a simple approach. If we have multiple GPUs, say we have been using a mini batch size of 10 images for this. If you have 3 GPUs, in effect, we are having a mini batch of size 30. Okay, so, well, maybe 30 is okay. But then there's a famous problem called large batch problem. Actually, it's a long-known phenomenon. So what it says is that if we increase the mini batch size, the overall accuracy stops improving. So this graph is from a recent paper published in 2017. So what it shows is that the best result were obtained when the mini batch size was 64. And if we increase the mini batch size to 2048, the accuracy, I mean, this is loss, so smaller the better. So it becomes worse. And so RIKEN, he's one of the 3 Turing Award winner of this year, based on the deep learning researches. He already pointed out this phenomenon in 1998. So this has been the obstacle for parallelizing deep neural network training. So say if we have like 2,000 GPUs, then mini batch size will be at least 2,000, 1 image per 1 GPU. And so this is a limit. So all of the recent results are in parallel deep neural network training are dealing with this large batch problem. Sometimes it's called large mini batch problem. It's kind of confusing. And this is a slide I've used 2 years ago at Colorado at the HPCS. And this was the state-of-the-art work at the time. It was using 128 GPUs and training less than 50 for ImageNet benchmark took 4.4 hours. And this was the best. And people are thinking this was the limit, because if we increase the mini batch size, the accuracy will degrade. But if I remember correctly, during the summer school, there was an update by Facebook researchers. So they succeeded in using mini batch size of 8,000. The training time was improved to 1 hour. And some months after that, the same group from Japan made a new record of 15 minutes with this batch size. And after that, there are some updates. It doesn't cover all of the updates. It only covers the main records. Tencent broke the record, and Sony did that last year, and Google did that one week after that. In the most recent results, it's from Fujitsu, and now it's 74 seconds. It's really a big improvement. And sorry, I don't have time to go into the details, but honestly saying, I don't like some of these researches because they are working on kind of ad hoc technique and doing parameter tuning, and well, it's very difficult to apply to some unknown problems. And so I partly don't like to do that myself, but these are based on something like warm start, efficient gradient distribution, hyperparameter tuning. But then one paper here, it's published last year. It's based on second-order optimization. There's a way of doing second-order optimization quickly, and it's developed by a group including TaiTech, NVIDIA, and RIKEN, and one of the authors is Matsuoka Sensei, who is the director of RIKEN R-CCS. And it makes it possible to increase the batch size to 131K. So it's a bigger improvement, I believe. Okay. So that's almost the end of my talk. This is just showing one of our recent work. We are working on combining search with deep neural networks, which is not for image recognition, which is for natural language processing, but we are trying to find a new molecule using these combinations. So we are using parallel Monte-Carlo tree search in combination of recurrent neural networks and combined with existing computational chemistry software. And we are working on the way of finding new molecules. And it's really a strong combination of search, deep learning, HPC is a really strong combination. So I hope some of you will get interested and try these things yourself. So why am I here? Because I've been working on parallel computing before, worked on some other topics like these are not related to wireless communication, biometric security. I worked on search and game and parallel processes, so that's why I'm here. I'm also in charge of the supercomputer at RIKEN AIP. It's a small one compared to K-computer or Fugaku, but it's a good one. It's ranked 4th in Green 500. I once wrote a book about computer Go, so I'm always looking for people who are interested in AI and has HPC background. Thank you very much.